Good afternoon. Thank you, everyone, for joining my topic. And thanks, Yannis, for the excellent introduction for Fluss and build the stage for me. And I'm going to continue the Lakehouse story for Fluss. And my topic is making your Lakehouse truly real-time. And a quick introduction of myself. I'm a committer and PMC member of Apache Fluss and the PPS member of Apache Fluss. Also original creators of Flink CDC and the Fluss projects. Currently, I'm leading Flink SQL team and the Fluss team in Alibaba Cloud. And my work also has a long centered on the distributed system for over 10 years, mainly on the big data computation and storage. Okay, I would like to begin my talk with a linking post from several months ago, an engaging discussion thread started by Good Morning that quickly gained traction on the network. And the topic is, what if we could rebuild Kafka from scratch? And I think it is very interesting question. What is the one thing that you would like to reflect most if you can rebuild Kafka from scratch? And this immediately took me back to 2 years ago when we were just starting the Fluss project, a project to rebuild Kafka. So my answer would be to be Lakehouse-native. So we want to build a Lakehouse-native Kafka. A Lakehouse-native Kafka is streaming storage that we can easily make your existing Lakehouse truly real-time by extending your Lakehouse with streaming abilities. But of course, Kafka is not a good fit for this use case. It is not a Lakehouse-native streaming storage. But here is why real-time Lakehouse matters. We can see that the traditional batch-oriented Lakehouse strive to meet the real-time demands. A typical traditional Lakehouse architecture is using, for example, Iceberg for the table format and use Spark for the batch ETLs on the Iceberg tables. So this generates usually days or hours latency, and this become a big limitation for real-time AI because data freshness will directly impact the quality and the correctness for the AI decisions. So ByteDance real-time AI-powered recommender for TikTok is the main difference with the other competitors. And the AI recommender relies heavily on the real-time streaming data. But because the system also will dynamically push the next video based on you just liked last second. So it depends heavily on your streaming data. But the existing Lakehouse is batch-oriented. It's usually hours or days latency. So ByteDance built their EB-sized Iceberg Lakehouse to add the real-time abilities on top of it to support their real-time streaming data for AI. So we built Fluss from scratch. This is an overview architecture of Fluss, a new Lakehouse-native stream storage. So Fluss will maintain a server cluster that provides sub-second latency stream read and write capabilities. It also has a tiering service that will continuously moving the Fluss data into Lakehouse data, like in Pymon or Iceberg or lines format. So the Lakehouse is used as a tiered storage for Fluss. And that means the hot data is kept in Fluss local storage for faster access, while the cold data will be tiered to Lakehouse to use the Iceberg format, Parquet file format, and to save the storage cost in a very cheap storage medium. And as it is also it is also a native Iceberg format. So all the existing Lakehouse query engines like Spark, Trino, Starworks can access the Lakehouse directly. It can just fit into your Lakehouse stack. And the powerful key feature here is we call it union read, which will truly unify the data streams and the data lakehouse. A union read means that you can read the combined data set of the hot data in Fluss and also the cold data in Lakehouse. It first reads the cold data in Lakehouse and then switch to the streaming data without any data duplications or data missing. So currently, the union read feature is already supported in Flink, and Starworks is working in progress. But here comes the question: why we rebuild Kafka from scratch? Couldn't we just enhance current Kafka to become Lakehouse-native stream storage? The short answer is very difficult, and the long answer is Kafka was designed for events, not for analytics and Lakehouse. So from the perspective of the architecture, Kafka is a very different system compared to Lakehouse systems. I think there are three key differences and the problems. This makes the Kafka very different with Lakehouse. The first problem is no schema, no built-in schema support. But Kafka treats every message as byte-array. This is very useful for microservice to communication between microservice. But these introduce are very limitations and problems in Lakehouse because it leaves the schema management to external tools. Like maybe you need to introduce a schema registry. And so Kafka also lacks the native schema support it will create many problems when moving topics to Lakehouse because you have to manually mapping the schemas fields, and it also you need to figure out how to do it when schema evolution. And the second problem is the data model mismatch. And I will go through this in next slide. The third problem is no update support. Kafka is append-only log model, so it doesn't support record-level updates. But updates and deletions are very critical features in Lakehouse systems, and you have to build or maintain additional ETL pipelines to materialize the append log into updated tables. This will increase complexity and the operational overhead. So these limitations makes Kafka is not a Lakehouse native storage. The integration of Kafka and Lakehouse will be very fragile, manual, and error-prone. It often requires per topic configuration, which will slow down our development. So this is a more detailed table to explain the data model difference between Fluss, Iceberg, and Kafka. We can also see some design decisions when we build Fluss and Kafka. So you can see that Fluss and Iceberg both treat the data as structured tables within databases. This is very helpful for data warehousing, that you can easily organize the tables into different databases. But Kafka, it only has one-level topics. This is fine for events, but not friendly for analytics. And both Kafka and both Fluss and Iceberg natively support partitioning. So partition by time or region or other any columns, and also support some partition pruning to according to pruning partitions according to the condition on the partition fields. This is very critical feature for efficient batch and streaming queries. And Kafka doesn't have the Lakehouse partitioning. The partitions in Kafka is a totally different concept. And the third thing is both Fluss and Iceberg supposed to update and delete rows, but Kafka is append only, and we have mentioned that before. And both Fluss and Iceberg support more than 20 data types. All the data types are aligned with each other. But Kafka doesn't have built-in schemas, so you have to manually mapping the fields, each one by one. And for the file format, Fluss uses Apache Arrow as the underlying log format, while Iceberg uses Apache as the underlying data format. Both are the columnar format, so they can convert and interoperate very efficiently. But Kafka commonly use Avro or JSON, which are raw format. It is very efficient for event-driven microservice, but not efficient for analytical workloads. So in a nutshell, Fluss is a Lakehouse-native storage, which aligns all the data model with Lakehouse systems. And Kafka, however, there's a big gap with the Lakehouse system. So what will this difference make? What will this make some difference? We can take a look at when we want to enable convert the Kafka data into an Iceberg. So if you have ever tried to string Kafka data into Iceberg, say using a product like Confluent Warp String, TableFlow, so you have this is a YAML file from the TableFlow quick start demo. You have to manually configure a complex YAML file to map the schema fields, the partition keys, the prime keys, and so on. Of course, this is very verbose and error-prone. And imagine you have not just one topic; you have hundreds, thousands topics, and each topic has over 50 fields to map. That will be a terrible work to do that. However, it is very simple in Fluss. You just need to turn on a single config using the outer table SQL statement, and this can save a lot of time for users. This is because we have aligned all the data models with Lakehouse, and is a Lakehouse-native storage. So we built Fluss since 2 years ago for this vision, and introducing the vision of stream Lakehouse. The streaming Lakehouse is to truly unify the data streams and the data Lakehouse to make them work like a single system. In this model, streaming and batch workloads can operate on the same data and with the same semantics. So since then, we've seen an industry trend that the data streams and the data lakehouse began to converge. In March 2024, Confluent announced the TableFlow. 6 months later, Redpanda announced the Iceberg topic. 4 months later, Stream-native announced the Author Engine. And 2 months later, AutomateQ announced the table topic. And in this year, Ivan announced the Iceberg topic. And now, I think it is very clear that the future is on the way to unifying strings and the lakehouse. So we are seeing a wave of Confluent, TableFlow, Redpanda, Iceberg, and blah, blah, blah. So all of them are aiming to moving Kafka topics into Iceberg tables. And we already know the limitation of Kafka, so they all extend the problems of Kafka. So we don't think TableFlow-like products are answer of the future. We believe Fluss streaming lakehouse is the future. So what's the difference between them? I think the principle of TableFlow is stream into lakehouse, but Fluss is streaming lakehouse. So stream into lakehouse is still a data synchronization tool that moves Kafka data into Iceberg tables. It is a one-way data flow, but the streaming lakehouse and the core value of stream into lakehouse is the 0 ETL, but it still keeps 2 copies of data, and user must to pay both for Kafka and Iceberg storage. And it also involves many manual configuration for each topics and each fields. So the biggest problem here is it still has 2 datasets. This goes against with the principle of lakehouse. So the principle of lakehouse is shared data. That means there's only 1 copy of data, and no additional ETLs, no vendor lock-in. You can use any different engines on top of the same data, like streaming engine, batch engine, AI agent. So all of them share the same data. So the Fluss streaming lakehouse is a shared data architecture. There is only 1 copy of data, and it is shared between data streams and data lakehouse. And the core value of stream lakehouse is to unify streaming and batch storage. So this can simplify your existing Lambda architecture into a unified stream and batch architecture. So you can just maintain 1 data set. So how Fluss built the Lakehouse-native streaming storage? I think the first is from topics to tables. Yannis has introduced that. Second is the first-class schema support. We have the schema enforcement for the table creation and the data ingestion. And the third one is that the prime key and updates. So tables in Fluss also have the prime key definition, and we use the LSM tree to efficiently support prime key and record level updates. And this can be updated in real time and in very large scale. And the prime key index is also very helpful to resolve the updates problems on Iceberg tables, because the data already have been updated and materialized in Fluss. And the fourth is the columnar string. So Fluss is a stream storage for analytical workload. We use the Apache Arrow as the underlying columnar log format, and it is very straightforward to convert the Arrow format into Parquet format in a very efficient way. And once all the core concepts and the data models aligned with Lakehouse, it becomes very straightforward to build a lake tiering service. The lake tiering service is a component of the Fluss cluster to responsible for continuously convert the Fluss data into Iceberg format data. So the data will it will continuously monitor the DDL's happiness in Fluss, and will automatically create corresponding tables in Iceberg REST catalog. And it also will automatically map the schema automatically between these 2 systems. And when we commit a snapshot of a lake table, we also will commit the snapshot ID and the corresponding log offset into both the Fluss metastore and the Lakehouse catalog. So this meta information ensures both the Fluss and the Lakehouse are aware of the consistent offset. And this offset will be used to union these 2 data layers. And And besides of that, it can also automatically detect small files and do the small file comparison automatically to help improve the query performance. So when carrying Fluss data into Lakehouse, we record the corresponding local offset in Fluss. This allows Fluss to check which portion of the system has already been offloaded to Lakehouse storage. So it is a safe point for Fluss to clean up the local data without losing data. So this capability is especially valuable for backfill operations. A common requirement in streaming processing to reprocess historical data, for example, several months. So the historical data already have been shared to Lakehouse, and we can reading the large volume of historical data directly from the Iceberg table with the help of the Iceberg I/O pruning. So all these I/O traffic will not go through the brokers. They directly reading the Iceberg table from S3, so it can reduce the broker overhead. But in contrast, Kafka will, if you reprocess historic data using Kafka, all the historic data will go through the Kafka broker, and this will overwhelm the broker and disrupt the leaf traffic. So it is very difficult to backfill data using Kafka. So this architecture makes Fluss to share historical data with Lakehouse and only need to store a very short-term data in Fluss. For example, maybe just a few hours instead of days. So this can reduce a lot of storage cost because you only need to save 10% data compared to before. And when carrying Fluss to Lakehouse, we also record the corresponding log offset in Lakehouse catalog. So this allows query engines to be aware where to read the delta logs based on the Iceberg table snapshot. For example, the query engines on the Lakehouse can perform a union read to combine historic data and the real-time data, and only a small window of logs need to be processed, and this will be a very efficient, usually only in seconds. So this is an in-depth overview of how union read works, and union read refers to the ability to query both historical and real-time data in a unified manner. So this example shows that a parameter key table with update operations via Fluss will record the change logs, and the lake tiering service will materialize the change logs in Lakehouse. So when a query engine reads from this table, it first retrieves the latest snapshot from Iceberg. So Jack and Judy in this case. And second, it will fetch recent change logs from Fluss from the given offset in the snapshot metadata. And this is an insertion of Timo and a deletion of Judy. And then it merges these two datasets and produces a final result. So the result is Jack and Timo. So you can get a complete and exact one's result using the union read. And in the future, we will implement a new union read implementation based on the deletion vector of Iceberg v3 to avoid the merge on reader cost and further speed up the query performance on parameter key table. So I think Lakehouse role in the real-time AI system should be to act as a low cost for historical data. However, we need to extend it to become a real-time Lakehouse to power all the AI applications. The first here is to be in the Lakehouse stack to just enhance your existing Lakehouse stack. It's not to replace anything. It adds streaming real-time abilities to your stack, to your Lakehouse, to make it become a real-time Lakehouse. And one more thing is that we have Iceberg and Apache. Actually, it's not good at handling multimodal data, but multimodal data is a key difference in the AI era. And Lens is a new open table format designed for multimodal data. So Fluss community and the Lens community work together to extend the Stream Lakehouse with Lens format. So with the new introduced the Fluss Python client, you can also connect the Fluss cluster with a Python ecosystem, writing images, embeddings into Fluss using a Python client. And then the real-time streaming data will be continuously converted into Lens format. So the integration of Fluss and the Lens is a powerful foundation for real-time multimodal AI to help to build multimodal AI applications that need to leverage the real-time data and the historical data. So if you are interested in this real-time multimodal lakehouse and the examples, you can check out the blog in LensDB website. And here is the current some status of Fluss. The Fluss was open sourced by Alibaba 1 year ago and entered the Apache Software Foundation as an incubating project in July this year. Since then, it grows very quickly. Now it has over 1,500 GitHub stars and attracting over 80 contributors from all over the world. And the community now is preparing its first release in the incubator. And Fluss is already in production at Alibaba, powering real-time analytical workloads and to replace Kafka when using with Flink. And especially, it is most Alibaba internal users using the column pruning and the Stream Lakehouse heavily to simplify their data architecture. And in some cases, it can reduce more than 80% storage costs. And now, Fluss manages over 3 petabyte size of data in Alibaba, and with cluster handling 40 GB size per second of the throughput traffic. And on Alibaba Cloud, we already have published a private preview managed service for Fluss. And we also have some customers on Alibaba Cloud to use Fluss, including from the EV companies to some gaming companies. And the future of Fluss, I think, including 3 directions: the real-time analytics, real-time lakehouse, and real-time AI. We are working closely with the Apache Flink community to co-optimize the entire real-time analytics stack from the computation to storage. As highlighted in Yanni's talk, the delta joins, streaming query pushdown, and queryable streams, and maybe more in the future. The second is real-time lakehouse. So our vision for Fluss is to become the real-time layer of lakehouse. And in the upcoming release, we plan to add more query engines like Spark, Trino, Starlocks to also support the Uniread and the Stream Lakehouse. And finally, Fluss is uniquely positioned to speed up the real-time AI workloads by serving as a feature store for the real-time feature engineering. And we also plan to support zero-cost schema evolution in next version, which is very critical feature for feature engineering, because features will be added and removed very frequently during the model training and testing. And okay, this is all my slide, and against this picture. Do we have time for QA? Okay, sorry. We can, if you have any questions, you can reach out to me off here. Okay, thank you.